When you pick up two magnets and bring them together, you feel a peculiar, silent resistance, an invisible cushion pushing back against your hands. If you flip one around, that resistance vanishes, replaced by a sudden, violent snap as they slam together. Your immediate instinct is to ask what that something is. You want to know what is actually happening in that empty space between the metal. But before we can talk about the magnets, we have to talk about how we ask questions. Because when you ask why about anything, you are embarking on a dangerous journey. You need a place to stand. You need to identify a set of things you already accept as true, or else you will find yourself falling forever in an infinite chain of why. Consider a simple accident. Why is your Aunt Minnie in the hospital? Because she slipped on ice and broke her hip. That is a perfectly fine answer for a concerned relative, but it isn't a final answer. Why did she slip? Because ice is slippery. But why is ice slippery? Now the ground starts to shift. You're told that the pressure of her weight melts a microscopic layer of water, so she was actually sliding on liquid. But why does pressure melt ice? Because water expands when it freezes, and the pressure tries to unexpand it. And why did she fall downward instead of floating away? Now you're into gravity and the curvature of space-time. Why did her husband call the ambulance? Because he cares about her. Why does he care? Now you're into biology, evolution, and the chemistry of the brain. You see the problem? Every answer is just a trap door, leading to a deeper question. If you don't pick a place to stand a bedrock of fundamental truth, you will eventually collapse under the weight of the inquiry. Most people want me to explain magnets in terms of something they already understand, something familiar. They want me to say there are invisible rubber bands connecting the two pieces of iron, pulling them together. But if I tell you that, I am lying to you. I am playing a con game. If I tell you that magnets work because of invisible rubber bands, you might feel satisfied for a few seconds. The image fits into your mental filing cabinet of how things move and pull, but that satisfaction is an illusion because eventually you'll realize the explanation is hollow. You'll ask, well, why do rubber bands pull back when you stretch them? To answer that, I'd have to explain the forces between the molecules of the rubber, which are electrical forces, the very thing I was trying to explain with the magnets in the first place. I would be running in circles, using the mystery to explain the mystery. It's a trick of language, not a transfer of knowledge. We have to be braver than that. We have to admit that electrical and magnetic forces aren't like rubber bands or springs. It's the other way around. Rubber bands and springs are like they are because of electromagnetism. These forces are the bedrock. In science, you don't explain the bedrock in terms of something else. You explain everything else in terms of the bedrock. We have to stop looking for gears and pulleys hidden under the hood of the universe because at a certain level, the gears disappear. Think about the chair you're sitting in or the table in front of you. You think of them as solid, permanent things. You think you're touching the wood when you rest your hand on it. But physics tells a different story. Your hand never actually touches the table. The atoms of your palm and the atoms of the wood get close, and the electrons surrounding those atoms begin to repel each other with incredible intensity. What you perceive as solid is just the sensation of those electromagnetic fields pushing back against your own. It is the exact same force you feel when you try to force two matching poles of a magnet together. The only difference is that you've spent your entire life pushing on tables and floors, so you've stopped wondering about it. You've accepted the table as obvious, while the magnet remains a miracle. But the table is just as strange. It's an electromagnetic hallucination of solidity held together by a force that is far more powerful than you can possibly imagine. When we call these forces strong, we aren't using the word the way a weightlifter or an engineer might. We are talking about something monstrously strong. To understand the scale of what we're dealing with, you have to compare electromagnetism to the only other force you feel every day, gravity. Gravity feels powerful because it keeps the entire moon in orbit and pins your body to the earth. but on an atomic level, it is a total weakling. Electromagnetism is stronger than gravity by a factor of 1, followed by 40 zeros. There isn't even a practical name for a number that large. If you were to hold two people at arm's length and somehow remove just 1% of the electrons from their bodies, the resulting electrical repulsion would be enough to lift the entire Earth. So, why don't we notice this monster? Why aren't we being torn apart or launched into space by these gargantuan forces? It's because atoms are perfectly, almost poetically, balanced. Every atom is a tiny fortress of neutrality, with positive charges in the nucleus and an equal number of negative charges spinning around the outside. They cancel each other out so perfectly that the force remains hidden in plain sight. Nature keeps its greatest power tucked away in a state of total equilibrium. But sometimes, the mask slips when you walk across a carpet and touch a doorknob, or when you comb your hair on a dry day and watch it reach for the comb. You've disrupted that balance. By rubbing off just a few billion electrons, a tiny, microscopic fraction of the total, you've created a small imbalance. And yet, because the force is so monstrously strong, even that infinitesimal leak is enough to create an effect you can see and feel from across the room. It can make pieces of paper jump off a table or cause a spark that you can hear. These are the tiny growls of the monster. Most materials, however, are like a crowd of people, all shouting different things at once. The noise just averages out into a dull, undetectable hum. But certain materials, like iron, have a secret. They have a way of organizing the chaos, a way of getting all those internal microscopic forces to stop fighting each other and start working together. In iron, the electrons are doing something copper or wood electrons simply won't do. It comes down to a property called spin. Every electron spins, and every spinning electron acts like a tiny, microscopic magnet. In most materials, these spins point in every possible direction, a chaotic mess where one electron's magnetic pull is immediately neutralized by its neighbor. It's total silence. But in a piece of iron, under the right conditions, these spins begin to line up. They cooperate. Think of it like a stadium full of people. If everyone is talking at once, having their own private conversations, all you hear from a distance is a low, meaningless blur of noise. But if everyone in that stadium suddenly starts chanting the same word at the same time, the effect is transformative. The sound waves synchronize, they amplify, and suddenly that collective voice can be heard miles away. That is what is happening inside a magnet. The electrons have stopped their individual chatter and started chanting in unison. When those trillions of tiny magnetic effects add up instead of canceling out, the force reaches out from the atomic scale into the human scale. Suddenly, you have a magnet, something you can hold in your hand, that exerts a physical influence over the space around it. This is why copper isn't magnetic, even though it has the same electrons and is governed by the same physics. In copper, the crowd never decides to chant together. The spins remain random, and the force remains trapped and balanced within the individual atoms. But iron allows for this grand alignment, letting us feel the raw strength of the electromagnetic field at a distance. But even this explanation, the idea of alignment and fields, is still just a description of the effect. To truly answer the question of what that invisible cushion between the magnets actually is, we have to go deeper than the iron itself. We have to look at what the electrons are actually doing to one another across that empty gap. We have to look at the three simple actions that govern every single interaction in our physical world. Because underneath the alignment and the spins, there is a fundamental exchange taking place. To understand the gap between those two magnets, we have to look past the metal and into the vacuum itself. At the most fundamental level, there are no fields in the way we usually imagine them. There are only particles interacting. This is the domain of quantum electrodynamics, and it reveals that the entire complexity of the universe is built upon just three simple actions. First, a photon goes from one place to another. Second, an electron goes from one place to another. And third, an electron emits or absorbs a photon that is the entire deck of cards. Every chemical reaction, every heartbeat, every ray of light, and every magnetic pull is just a different arrangement of these three moves. When you feel that magnetic resistance, what you are actually experiencing is a frantic, high-speed exchange. Electrons don't just sit there. They are constantly throwing things at each other. They exchange what we call virtual photons. I don't mean light you can see with your eyes. These are packets of energy that exist only for the duration of the interaction. You can never catch one in a jar or look at it directly, but they are the messengers of the force. One electron in the first magnet throws a virtual photon, and an electron in the second magnet catches it. Imagine two people on ice skates throwing heavy medicine balls back and forth. Every time one throws a ball, they are pushed backward. Every time the other catches it, they are pushed backward too. From a distance, it looks like an invisible force is driving them apart. That is exactly what is happening between your hands. Trillions upon trillions of these virtual photons are being swapped every second, creating a microscopic bombardment that translates into the macro-scale pressure you feel against your fingers. It sounds strange, almost like a fairy tale, to think that solid objects interact by throwing invisible light at each other. But there are no gears underneath this process. There is no hidden mechanism of springs or strings. This exchange of virtual photons is the bottom of the well. It is as deep as the explanation goes, and it is the same mechanism that allows us to master the world through the unification of electricity and magnetism. The realization that electricity and magnetism are not two separate mysteries, but two sides of the same coin, was perhaps the greatest turning point in human history. In 1873, James Clerk Maxwell wrote down the equations that finally unified them, proving that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric current. This isn't just a fact for textbooks. It is the reason our civilization functions. It means that we can take the energy of a falling river, use it to spin a massive wheel connected to a coil of copper wire near a piece of iron, and cause electrons to dance. Think about the sheer scale of that dance. Because the copper moves near the iron at a dam hundreds of miles away, electrons start moving in a wire. That motion travels through thin lines stretched across the landscape, into your city and into your home, and at the other end, that movement is fed back into another arrangement of copper and iron, turning that electron flow back into the spinning motion of a fan, the heat of an oven, or the light in your room. All the wheels in a city turn, because one wheel at the dam is turning. They are all locked together in a synchronized performance, connected by nothing but the fundamental nature of the electromagnetic force. It isn't complicated machinery or a special magical substance doing this. It is just the basic behavior of the bedrock. You move iron here, and iron moves over there, far away, because they are led by the exchange of photons through a wire. What a fantastic thing nature is. We have built our entire modern existence on this one realization. Every light that turns on and every motor that whirs is a testament to our understanding of how electrons and photons interact. But the truly remarkable thing isn't just that we can use it, it's the precision with which we can predict it. We aren't just guessing about how these virtual photons behave. We have developed a way to calculate their actions with a degree of accuracy that borders on the unbelievable, a precision that makes every other science look like a rough estimate. We can calculate the magnetic properties of an electron with such staggering accuracy that it challenges our very understanding of what a fact is. We don't just estimate or get close. We use those three simple actions: the photon moving, the electron moving, and the emission or absorption, to add up every possible path a particle can take. When we compare these mathematical predictions to what we actually measure with our most sensitive instruments, the results match to 10 decimal places. To give you a sense of that scale, it is like measuring the distance from Los Angeles to New York and being accurate to less than the thickness of a human hair. This is the most precise prediction humans have ever made about anything in the history of our species. It is the ultimate proof that we have found the bedrock. This kind of accuracy doesn't happen by accident, and it doesn't happen in fields that are still guessing about their foundations. It happens because we are finally looking at the fundamental machinery of reality. However, getting to this level of precision wasn't easy. When physicists first tried to use quantum theory to calculate these forces back in the early 20th century, the math broke. Every time they tried to account for all those virtual photons being exchanged, the equations spit out infinity. In the physical world, infinity is nonsense. It means your theory is failing. It wasn't until around 1948 that a solution called renormalization was developed. The breakthrough was realizing that we never actually see a bare electron in isolation. What we measure is always the electron plus the cloud of interactions surrounding it, the constant storm of photons being emitted and absorbed. By absorbing those infinities into the measured values, the math suddenly cleared up, and the predictions began to match reality with that human hair precision. Some people at the time thought it was a con game, a way of hiding the flaws in the math, but the results were undeniable. Nature seemed to be telling us that the interaction is the thing, but even with this perfect mathematical grip on the world, a massive unexplained shadow remains. There is a number that governs the strength of this entire force, a number that we can measure but cannot explain, and it is the reason you and I exist at all. This number is 137. More specifically, it is the fine structure, constant, approximately 1 over 137. It is the number that determines exactly how strongly an electron will catch or throw a photon. It dictates the intensity of the electromagnetic force, the pull of the magnets in your hand, and the strength of the chemical bonds holding your DNA together. If this number were even slightly different, if it were 138 or 130, the universe as we know it would vanish. Atoms would fail to hold their shape, stars would burn out differently, and chemistry would be rendered impossible. It is one of the greatest damn mysteries in all of physics, because we have no idea where it came from. We didn't derive it from a deeper principle. We didn't calculate it from the three simple actions. It is simply a value we had to measure and write down. It is as if someone dialed the universe to 137 and then walked away without leaving an instruction manual. If you ask why this number exists, science has no answer. We have reached a point where we can predict the behavior of a magnet to a hair width across a continent, yet we are left staring at this number like a locked door. This brings us to the limit of our intuitive understanding. We want a picture of what's happening. We want to see the electrons spinning like a tiny planet, or the photons flying like little bullets. But the deeper you go into the bedrock, the more the pictures fail. Electrons don't behave like tiny balls. They aren't fogs or waves in any sense that your brain, which evolved to dodge rocks and find fruit, can visualize. Our brains were never designed to see the quantum world. We have the mathematics, which works with monstrous precision, but we have no mental image that isn't a lie. The machine of physics calculates the results perfectly, but it has no picture in its head. It just does the arithmetic. We have to accept that nature, at its most fundamental level, is genuinely different from anything we are equipped to imagine. We have to be content with the fact that while we cannot visualize the mechanism, we have mastered the rules of the game. This reliance on mathematics over mental imagery is a hard pill for most people to swallow. We feel that we don't truly understand something unless we can build a model of it in our minds, a little mechanical theater where we can see the parts moving. But that desire for a picture is exactly what leads us back to the misconception of invisible rubber bands. It is a craving for the familiar. We want the quantum world to act like the macroscopic world, but nature is under no obligation to satisfy our intuition. In fact, the very things we find intuitive, like the way a ball bounces or the way a spring pulls, are only intuitive because we've experienced them since birth. We forget that those experiences are actually the complex end result of trillions of quantum interactions we can't see. If you want a clear picture of what is happening inside a magnet at the atomic level, something you can truly visualize, I cannot give you one. Nobody can. What we have instead is a spectacular, rigorous honesty. We have the ability to state exactly what will happen and have it be true. This is the difference between philosophy and experimental science. In science, if the calculation agrees with the experiment, and if it does so with the precision of a hair width across 3,000 miles, then the theory is right. It doesn't matter if it's weird. It doesn't matter if you can't draw it on a chalkboard. Physics is the ultimate show-your-work discipline. You don't sit around waiting to understand every mystery perfectly before you start building. You learn enough to predict what happens. You test those predictions against the harsh reality of experiment, and if they hold up, you use them to build the world. That damn turning wheels across the city works because we understand the electromagnetic bedrock well enough to manipulate it. We don't need a mental picture of a virtual photon to make the lights turn on. We just need to know how they behave. And when you finally stop trying to force the universe to look like a collection of springs and gears, you realize that the answer to your original question about magnets was sitting right in front of you the whole time. So we return to the moment you first picked up those magnets. You felt that invisible something and you asked, "What is that?" You wanted an answer that sounded like something you already knew, something like rubber bands or invisible strings. But now you see that the question was actually inside out. Magnetism isn't the mystery that needs to be explained by the familiar world. Magnetism is the explanation for the familiar world. Every time you've touched a surface, felt the wind on your face, or looked at a solid object, you were feeling the electromagnetic force. You've been swimming in it since the day you were born. Magnets are simply nature being honest with you for a moment. They take the force that usually stays hidden behind the perfect balance of atoms, and they make it obvious. They let you feel at a distance the same monstrously strong power that holds your own body together. When you feel that push or pull, you aren't feeling a strange anomaly. You are feeling the bedrock of reality. You are feeling the collective chant of trillions of electrons in a piece of iron, communicating through the exchange of virtual photons. It is a spectacular, invisible dance that follows just 3 simple actions, governed by a mysterious number we call 137. There are no gears underneath. There is no deeper mechanism hiding behind the curtain. This is how it really works. The fact that we can describe this force with such incredible precision that we can predict the behavior of an electron to the width of a human hair across a continent is not magic. It is the result of human beings finally learning how to pay attention to what nature is actually doing, and writing it down carefully. We have found our place to stand. So, the next time you pick up a magnet and feel that mysterious resistance, don't think of it as a puzzle to be solved. Think of it as a rare glimpse into the fundamental machinery of the universe, a moment where the invisible becomes tangible, and the bedrock shows its face. That is the honest answer. That is why magnets work.